what is the probability of the union of two events that aren't necessarily disjoint? So the axioms tell us that if we have two events that are disjoint, the probability of their union is the sum of their probabilities. But if we have two events that aren't disjoint, what's the probability of their union? Well, the way we can figure this out is by partitioning their union. And this is easiest to see with a picture. Okay, so A union B is that, right? Okay, we're going to divide A union B into, we're going to partition it into three subsets. Okay? One of the subsets is going to be the stuff that's in A but not in B. So how do I write that in symbols? What's stuff that's in A but not in B? Okay. A minus the, so we don't really have a notion for subtracting sets yet. There is such a notion, but we don't have that. It is in A and not in B, right? A, B complement. That's stuff that's in A and not in B, right? Okay, so that's, if you like, that's this stuff, right? That's A intersect B complement. Okay. Then what's this stuff over here? Okay. So I'm going to write it A complement B, but it's the same thing. And then what's that stuff? AB. Right, A intersect B. All right. Are these mutually exclusive? Are these disjoint? Yeah, okay. Suppose I'm in AB complement. Then I'm not in B. Both of these, to be in either of these, I have to be in B. Okay, so if I'm in this, I'm not in either of those. Right? Suppose I'm in this one. If I'm in this one, I'm not in A. If I'm not in A, I can't be in that or that because those require me to be in A. Right? Okay, so these three are mutually exclusive. If I'm in this one, I have to be in both A and B. In this one, I'm not in B, and in this one, I'm not in A. Right? So I can't simultaneously be in any pair of these things. There's no way for a dart to stick simultaneously in any two or more of these three sets. If I thought of this as a dartboard, I can only stick in one. Okay, so by the third axiom, the chance of A union B is the chance of this plus the chance of this plus the chance of this because these three are disjoint. Okay? It's like area. If I thought of these things as the area of a subset of this rectangle S, the area of this union is the area of this piece plus the area of this piece plus the area of this piece. They don't overlap. Okay? So the probability of A union B is the probability of this plus the probability of this plus the probability of this. So far, so good? Okay. Now, what happens if I take P of A plus P of B? I hate dividing the work across the screen, but what's P of A plus P of B in terms of the pieces that we've got over here? Well, I can write A as the union of this piece and this piece, right? It's the stuff that's in A but not in B, union the stuff that's in both A and B. So A is this piece, union this piece. Similarly, B is this piece union this piece. Okay? So I can write A, that's the probability of AB complement union AB plus the probability of A complement B union AB. Right? Because that's just another fancy way of writing A. That's a fancy way of writing B. But this and this are disjoint. And this are disjoint. So the probability of this union is the probability of that plus the probability of that. And similarly, probability of this union is probability of that plus the probability of that. So what is this? This is P of A, B complement plus P of AB plus P of A complement B plus P of AB, which is P of AB complement plus P of A complement B plus 2 probability of AB. Right? If I take the area of this plus the area of this, I've counted the area of the intersection twice. So the area of the union, I got to subtract off one of those intersections because I counted it twice. So this thing, this sum, is the same as that, except this only counts the intersection once. Right? So what we've just shown is that somewhere here in the missing board space, for any two sets whatsoever, probability of A union B is probability of A plus probability of B minus probability of the intersection A and AB. Okay? In the special case that A and B are disjoint, A intersect B is empty. The probability of the empty set is 0. So in the special case that A and B are disjoint, this reduces to the third axiom. When A and B are not disjoint, we get this extra thing to subtract. Now, I just said that the probability of the empty set is 0, and that's actually a result which we haven't proved, but it follows from the complement rule. Right? Complement rule says probability of A complement is 1 minus the probability of A. So what's the probability of S complement is 1 minus the probability of S, which is 1 minus 1, which is 0. What's S complement? The empty set. Okay, so the probability of the empty set is 0, probability of S is 1.